passion for glory. Don't lose your grip on the dreams of the past. You must fight just to keep them alive. It's the eye of the tiger, it's the thrill of the fight, rising up to the challenge of our rival. And the last known survivor stalks his prey in the night, and he's watching us all with the eye of the tiger. Face to face, out in the heat, hanging tough, staying hungry. They stack the odds, so we take to the street. We'll kill with the skill to survive. It's the eye of the tiger, it's the thrill of the fight, rising up to the challenge of our rival. And the last known survivor stalks his prey in the night, and he's watching us all with the eye of the tiger. Here they come. Rising up, straight to the top. Had the guts, got the glory. We're at the distance now, I'm not gonna stop. Just a man with his will to survive. It's the eye of the tiger, it's the thrill of the fight, rising up to the challenge of our rival. And the last known survivor stalks his prey in the night, and he's watching us all with the eye of the tiger. Wow. Is it magic time?
It looks like it is.
I think it is.
It is.
Wow. You ready?
I am. Are you?
Mostly.
Mostly?
Yeah.
Come on.
All right. Welcome, EECS16A. Woo!
Nice.
So nice to have people here, huh?
Yeah, it's very nice to
Yeah.
have people.
So nice. Thank you all for coming, even though you don't have to, but we still do appreciate that you come.
Very
Because
much.
we definitely think that this is the best way to do learning
To learn.
and catch up with classes, because guess what? Tomorrow there's a
Oh, yeah.
discussion. No, on Monday there's a discussion. Well, maybe those
There's
could
no
actually
class tomorrow.
There's no class tomorrow?
No, we canceled.
Oh, yeah. Oh, I'm sorry. I can't come tomorrow. Class? There's no class tomorrow.
But you do
Tuesday.
have a pre-lab reading that you are supposed to do, because now next Monday you start labs.
Ooh. Ooh.
Oh, yeah.
Ooh.
So
Wow, the labs.
this time we didn't put pre-lab reading in the homework, but going forward we're going to make sure that that's part of your homework, because we really, really, really want you to read what you're going to do in the lab before you go there. And actually, when you start working in a lab, if you start working in a lab, this is part of safety protocol to go to the lab. You have to be
Dead? Aww. So, oh, this. I'm just trying to repeat what you're saying. Yeah. I don't like those batteries. Here we go. We need a power source. What's called a voltage source in this particular case. Implement it as a battery.
Hello? Oh, that's too. Hello? Okay. There we go.
Life is a connector
I'm
problem.
back. Yeah, so as I was saying, when you go and work in the lab, reading about what you're going to do is part of safety protocol, because you want to be aware of what's going to happen to avoid any type of accidents. Okay, so today I'll be doing the talking, or most of the talking, and we are going, this lecture is, you would say it's out of order, but we really think that it's better to give you an introduction of the circuits before you go into the lab, because you're going to be doing some of the stuff that I'm going to talk about here today. So before, this class is really about design of information devices and systems. And a big part of a system is the hardware that goes into it. And that's why this class is so special, because you get to see the math and the software and the algorithms and the games that go into a system design. Okay, my pants really don't want to take this. Okay. Into a system design, but we also have to look at the hardware. And how are we going to connect things and connect all the electronic devices such that you get the performance that you want from your system. So you have this on your notes, this figure on your notes, where we have, okay, here's the real world. We have all sorts of sensors in the real world. We have to have some electronics that measure the signal that you are getting from the sensors. And then those signals are processed through algorithms. And those algorithms are also being processed very fast because of the hardware that we have. The computers are faster and faster. That makes us have faster information. So in this module 2, which is known on the streets as the circuits module, you will have just more tools for your design. And I want to just show you a little bit about the types of tools. So in the analog world, which is the world that we live in, there are many things that are happening. You might want to measure the temperature in this room, especially last week. You might want to measure movement. Maybe we want to count how many people are here for presence in lecture, maybe. Or it could be more sophisticated things where you are monitoring, for example, vital signs of a person that is in a hospital bed. So you are taking all these signals, and this is taken by sensors. And the sensors will perform better if, first of all, you know the range of your data that you need to measure. What's the accuracy that you can have in the measurement? So let's say if in the lab I want to develop a thermometer, and my application is to stick this thermometer in my skin and measure skin temperature. So what are the important ranges of temperature that I have to optimize that sensor for? Well, about maybe 35 degrees Celsius to 42, because if you get to 42, you have fever, well, you should do something about it. But if I'm also developing a temperature sensor that now I want to monitor how vaccines are shipped across the country, then the ranges of temperatures are way different. So you have to optimize your sensor, not only the hardware, but also the software that you're going to use for those limitations. And of course, this allows us to have very cool applications, such as the self-driving car that you saw in the very first lecture here. Okay, and then there's the processing. The processing is the tools that you're getting for the processing are coming from Module 1 and Module 3. We are aware that many of you have seen some of the material from Module 1 before, but it's going to pick up. So keep coming to lecture because the pace gets faster. And then a system could actually have actuation. So after you process the data, the next step would be, so let's say we were measuring the temperature in this room. and then we decided that the temperature was way too high, humidity was high, people were not comfortable, then the actuation would be, okay, air conditioning comes on and it will blow cold air in certain points, which I was trying to find. I was walking around so I cooled down, and then to a certain temperature, and then the air conditioning turns off. So this part of actuation you're going to learn if you take 16B. Okay, but I wanted to give you a different system. This is a system that I worked in my lab because it's a bit different from what you will see normally. So in this system, the first thing, you find a problem. We as engineers, we are always looking at problems because we want to make things more efficient, right? So our job is to look around and see, look, there is a problem here. How can this be better? So here's the problem that we worked on. We worked on electromyography. What's electromyography? You measure the signals that you can get when your muscles are moving. Why is this important? Well, this type of measurements have a huge impact on rehabilitation. So if someone needs to retrain after an accident, needs to retrain the movement of limbs, legs, arms, it is useful to have models that could give some signals for an artificial limb or a device that provides you with the energy that you need to relearn those movements. So this is by providing some actuation. But first you need to learn how this movement happens in the first place. So the systems that are available today look like this. So imagine yourself, you need to learn to walk, and the doctor provides you with this system and says, okay, I know you are in pain, but let's walk around dragging all these wires and then having all these electrodes stuck to your legs or to your arms. Is this the best solution? No, right? So when put in front of you, you can recognize that this is not the best setup for a person that needs rehabilitation. Okay, there are other problems. You see that the electrodes are all far away from each other. That means that the resolution of the data that you're going to get is not very fine, not refined. In our movements, if you move your hand and pay attention to all the muscles that you have in order to make that movement, there are very fine muscles that are responsible for your mobility. So we said, okay, here's the problem. The problem is the electrodes are very bulky, accuracy in the reading is terrible, and the computation now is always done in an external device, which typically is a laptop. So this person would be carrying a cart with a laptop measuring the data. Okay, so we came up with a solution to use a different type of electrode. So I'll show you a video that doesn't work in that platform there. Let's see if it works. Okay. So this is what we developed in the lab. I told you in the first class that we work on printed electronics. So what you see here is the scientist or the engineer mixing silver, which is a conductor, and this is a screen printer. A screen printer is used to put graphics on t-shirts. You will use this for your clubs. Okay, but here you have electronic material. Okay, so what we did, we designed a set of electrodes that are quite small, 64 of them, that would fit perfectly in the arm of the graduate student who is doing this research. This is in a flexible substrate, as you can see. You can see the dimension. The idea was that we were going to wrap around the arm, as you see here. Collaboration with Professor Jan Rabai, we used a chip a microchip that was developed here at Berkeley that uses very low energy and transmits data wirelessly. And the students also worked on machine learning algorithms to train the system. In Module 3, you're going to start tiny bits of machine learning, or at least the foundation, some of the foundation. So they created a classifier. Classifier, as you need a circuit and an algorithm. They work together. So in this, you have a system that is learning the recognition. The only thing that we didn't figure out is the ground, and I'll teach you what a ground is, which was in the elbow of the student. Okay, we did more sophisticated algorithms. We were able, in the end, I'll go back to my other platform. In the end, we were able to define 16 movements on the hand, very fine movements, which was the way better than anything else. So the point is, you are taking this class because you want to learn to design things. And design of electronic systems, especially for information, takes both hardware and software. Okay, and so that's why in Module 2, you are going to learn how to analyze circuits. Some of you might have done circuits before. Here, the methodology is a bit different than it's used in high school and what's used in circuit classes later, because we really want to give everyone the tools so that you can go from a circuit like this, where you have a battery, a resistor, and an LED, and then you form a model, and with that model, you can predict and you can model how that circuit is going to behave under different parameters. And vice versa. You might also want to have a model that tells you how you wish that your circuit would be behaving, and then you collaborate with someone that is really good at making circuits and took all the circuit classes, and you fabricate that circuit to give the response that you had in your model. So vice versa. And so we are going to give you a very nice method that allows you to do this analysis of circuits. Okay, so basically, these are tools that you are going to carry as you go through your studies here. And the circuits that we're going to study or analyze in 16A are all linear behaving circuits, and the tools that we are going to use to form the algorithms to analyze those circuits, so you use linear algebra, which is what you are studying in Module 1. Okay, but first, I want to have a little science review, because there are a few things that sometimes we take for granted, and we studied in high school and then we forget about it, but I want to remind you so that you have the basics here and the vocabulary to talk about these circuits like a well-informed person. So, remember the periodic table? Yeah? Gives you a lot of information, right? Gives you information that is related to what the materials are all about. What is our world made of? We look around. Materials everywhere, atoms of different type. Atoms get together, form a new compound, you can have a different material. So everything that we have around here is made of atoms, including ourselves, that have some properties. Part of the things that you studied when you were looking at this periodic table was the atomic number. Does anybody remember what the atomic number was? Go ahead. Number of protons and electrons that you have in an atom. Well, those are charges, right? So you have charges in every atom. You have positive charges and you have negative charges in every single atom. Okay, so if you remember, oh, you can have such cool pictures of the atoms where you have the nucleus and then you have the electrons all orbiting around the nucleus of the atom. And you know those beautiful electrons that are orbiting, they are very, very important for electronic devices because those charges are the only charges that can move. And if they can move, they can form something that's very important in electronic devices, which is current. So current in an electronic device is just electrons moving from one point to the other. Who tells the electrons where to move?
Me.
That's right, Mickey. You are a driving force for electrons. And we are going to prove this in a moment. So, here, a little bit more of science review. Remember those things you had to do in chemistry? I loved them. Oh, they were so relaxing. Okay, and we had to fill up these orbitals with electrons. How many electrons can you have in one orbital? 2. But what's special about the occupation? They have to have different spins. Exactly. You can never fit more than one electron in these orbitals. What are orbitals? Orbitals are placing energy. It's a state of energy. So only one electron with, or 2 electrons with a different spin can occupy one state of energy. Okay, and then depending on how many electrons you had in an atom, then you would go 1s2, 1, and then, oh, very relaxing, yeah. Remember that, okay? So we have electrons everywhere. The electrons can only occupy one state of energy. And we need the electrons moving in order to have current. Okay. Now, a little bit of advanced method. So first we review what you learned in high school. Now, sometimes we know this just jargon, but I want to put into context of electrons. So the materials that we are going to use in this class, are, let me mark here, 16A, I'll use Mickey's favorite color. In 16A,
Pink?
Pink. In 16A, we are going to be looking at conductors and insulators. Okay. If you like devices, like I do, I'm using my favorite color, then you learn about semiconductors if you take 130, 134, 143. Okay. So, let's talk about these materials. There are classes of materials. They are classified as conductor, semiconductor, and dielectric or insulator, depending on how the electrons behave inside that solid now. And a solid, let's say a conductor, a piece of a wire, it's just a bunch of atoms that form that solid. So in a conductor, there are many, many electrons. There's electrons everywhere. But those electrons are just free to move. So let me give you an example. So if I take row A here, I'll say, look, if row A is formed of a conductor and all these students are electrons, I can tell them, please move. Please move. Yeah, I mean it. Move. You can go wherever you want. Yeah? Please do it. Electrons, oh, they are reluctant. Yes, I mean it. Yeah, yeah. Move, move, move. Walk around. Yeah. Uh-huh. They needed some driving force. You too, you're also an electron. Yeah, yeah. Go ahead. You can move wherever you want. Yeah? Okay, except him. You can stay. Yeah. All right. Electrons, you can move back.
See you on the midterm.
Huh? He's in a localized state. In solid state
he's part
physics.
Of the valence. He's part of the valence band.
Exactly, yes. Okay, so that's the conductors. Free to move. Plenty of electrons to move around. Semiconductors, a little bit different. Most of the electrons are in a level, in an energy level that is where they can be relaxed and with the lowest possible energy, using the lowest possible energy. And in that state, the electrons are so-called, they're occupying a band of energy that's called valence band. They don't move there. So let's say if you're an electron, you're pretty much in your lowest possible energy level. If you're sleeping, oh, you're in deep levels of the valence band, lowest possible energy, right? Now, in order for you electrons that are all in the valence band, with the exception of 2 lonely electrons here that are moving in this semiconductor, in order for you to move, you need to gain some energy, right? Otherwise, you're just going to stay where you are. Okay, so let me give you that energy. Stand up. Everybody. Feel what it takes for an electron to go from the valence band to the conduction band.
What?
Yeah, stretch, move. Now that we are all here in the conduction band, do you feel like it's easier to move or more difficult to move? Easier, because you are already in a state of energy that is much higher. You're even talking, you might even haven't woken up, right? Okay, now if I tell you, relax. There you go. There you go, you go back to the lowest possible energy that you have. You went back to the valence band. Now, what do electrons do when they go from high levels of energy to low levels of energy? Where does that energy go? Sometimes they emit photons. So imagine if you were true electrons, when you sit down, there's light going through the, oh, beautiful. Huh? Other type of energy, heat. That's right. Some of the energy is given out as heat. Sound, electrons, sometimes if they move something that makes sound, yeah. Very good. Radiation, some electrons give radiation. Excellent. Okay, so that's what happens in a semiconductor. Now, in an insulator, if you are my electrons here in the valence band, in order for you to become an electron in the conduction band of an insulator, I would have to tell you, now fly. Touch the ceiling. Can you? You can't.
You need my stick.
Yeah, you need your stick and then you can, yeah. Why you can't? Because you need a much higher energy in order to get to those levels. And this energy that you have to overcome in order to become a free electron, an electron that conducts energy, conducts electricity, you need to overcome that energy gap. That energy gap is called band gap. Band gap because it's the gap in energy between valence band and conduction band. And that is huge in insulator. So insulators do not allow electron movement, because it's very hard for the electrons that are in that material to move because the energy levels that are needed are way too high. If you apply, okay, I'm not going to say that yet. Now, all these electrons, in order for them to become useful for us, the electrons, the exercise that we did here, it was not useful, right? You stood up, okay, you woke up a little bit, but then you sat down, and the energy that you gained, you just released. in semiconductor devices or in electronic devices, we want the electrons to move from one place to the other. And in order for that to happen, a driving force is needed. So, Mickey, are you sitting in row E?
Oh, yeah.
E for electrons?
Oh, yeah.
Nice.
Suddenly,
so
it's like
everybody sitting in row E, now it's going to be an electron. And Mickey, let's stand up. There we go.
Come on.
Stand up, stand up, stand up. And Mickey is going to be a driving force. Okay? I just gave you energy to stand up. Now Mickey is going to create current by being a driving force. Take it away, Mickey.
High voltage, low voltage, like medium?
With these electrons, I think you can start with high and see.
I'll start with low and see what happens.
Yeah.
Can you please move?
Oh, low
please?
energy.
Please, can you slowly, can you please
where?
move?
Move where?
Just over there, push, push, you know, and then go up, go up. Come on. All right, increase the voltage. Come on, come on. Come on, move, 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 move. Move, 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 move. Come on.
Very good.
There you go. Woo.
Uh-huh.
All right, come on, come on, come on, come on, come on. Come on, you can do it. You can do it. You can do it. Hold on, hold on. Electrons. Hold
the
on.
driving force stopped.
All right, come on, come on.
Hold on. I have a question for the first electron. Why did you go that way?
Yeah, well, where'd you go that way?
Tell me, why? It was longer, but why didn't you go through the rows?
Yeah, yeah. How about we try? Turn right here. Turn right. Turn right. Okay, go through. Go through. Come on. Come on! Come on! Move, 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 move. Move, 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 move. Wow, they're so slow.
They are.
So hard to move through
that?
this thing.
Why is
Whoa,
that?
what a resistance.
Yeah.
And then go down fast. Go down fast. There you go.
Very
All
good.
right. Back
Let's
in E,
see.
back in E.
You can occupy your states of energy again.
Come on, come on, come on.
Let's see if they're going to go the easy way or the hard way. With resistance or without resistance? Some chose the path without resistance. Others the path with resistance.
Oh, look what happened.
Yeah. Oh, Vicky.
Wow.
You arced.
So much voltage it arced. That's
Very
funny.
good.
That's funny.
I know. See, I can make jokes sometimes.
Wow.
Okay. So, what's the point of this exercise? Apart from keeping Mickey entertained. If we have electrons and we give the electrons a driving force, they will move. But there are paths that were easy, right? And that's why our electrons from row E went all the way to the back where there is no resistance. And then they can start coming down here this corridor where there's no resistance. And was it hard to go through the other people? You had to move some electrons, right? Because some levels of energy were occupied. And you as an electron cannot be in the same level of energy. So there are materials that will allow this energy, these electrons passing, a current to happen very easily. Other materials will be more difficult. And you can make things either easy or more difficult in your designs. Okay, so what are the electrical properties that we know of? First here, our electrons moving, what is that? Current. Very good. Current. And current is just the flow of electrons. What's the analytical symbol for current? It's an I for current. And what is the unit that we use to measure current? Amps, amperes, amps, amperes. Very good. So what's current is the flow of charge, the flow of electrons. Can be through a metal, could be through a semiconductor. Can it be through an insulator? No. Thank you. Second quantity that we saw here, what was Mickey? Our driving force. It was the voltage. Very good. Thank you, Mickey. You're the best.
Thank you.
The voltage.
No, you're the best.
That's right.
Yeah, you're the best.
What's the analytical symbol? V for voltage. And what's the unit? Volts. Volts. For someone who studied this and was humble enough to name it after himself. Okay, volts. And then what's volts? Is the volts or the voltage is always applied across something. So in our joke here, I could be the driving force together with Mickey, and then I would come here to row E. Mickey would go to the other side of row E, and then we would apply the voltage across. Ready? Let's start with low voltage.
Who's positive? Who's negative?
No, we are going to do it together. Low voltage first. 1, 2, 3. Can you please
move?
stand up? Yeah. Okay.
Please.
Now, can you please come on? Let's speed up. I have to finish this class. Higher voltage.
Oh, come on,
Come on. No, we'll be back.
Come on.
So voltage is always applied across, okay? Across an element. So if they were our wire, we would apply a voltage across, or if they were a resistor, because it always took a little while, we would apply across. Next quantity that we are going to study and become experts on is resistance, which our electrons experienced. Resistance. What's the symbol? R. Very good. And the unit? Ohms. Ohms. Very good. And what's the definition of resistance? If current is flow of electrons, what's resistance? Just shout. Yeah, it's an opposition to the flow of electrons, or an opposition to flow of current, or current flow. Yeah? Very good. Okay. So, what are you going to do in the lab? Your first lab next week is the imaging module. And then, so you are going to use a lot of the things that you learned in module 1 to play around and form some images. It's pretty cool. Then in the second lab, or the second topic for the lab is a touch screen, which is pretty nice, where you are going to do 2 modules for a touch screen. And then last, towards the end of the semester, you're going to do acoustic positioning. And these concepts of voltage, current, resistance are going to come over and over again. And the circuits that you're going to be using are going to become more and more sophisticated. So, in real life, what you're going to see in the lab. So in your kit, your lab kit, when you receive that, there will be wires, like these ones here, wires with connectors. In those wires, you are going to represent the wires in a circuit just as a line like this. This is a wire. You're going to have capacitors that look like these ones. What do capacitors do? They store energy, they store charge. Yeah. Are they like batteries? No, no. Because what do batteries do? They produce, right? They give you the charge. Yeah, capacitors store the charge. Okay, so capacitors. What's the symbol for a capacitor? It's, we use 2 parallel plates like this as a capacitor. In module 2, we're going to talk a lot about capacitors. You're going to have, instead of a battery, you're going to have a very expensive, very sophisticated power source. which in our circuit analysis, we are always going to say voltage source is a power source. In the voltage source, we are going to always write in our circuits like this. It has a polarity, and you can set the voltage. So when we said, oh, let's start with low voltage, you can increase the voltage. Now, you can see here is displayed 25 volts. That's more than what you have in your battery, right? It depends on the current that you are setting in this box. You can have a totally safe high voltage if the current is very low, but we are not going to go to high voltage, so you're going to fry things that are in the lab. So read your lab very carefully, because you don't want to see the black smoke. And the black smoke, right, Mickey? It's what it makes everything work.
Yeah, black smoke is the thing that makes electronic circuits work.
Yeah.
And when it comes out, they stop working.
Yep. Exactly. And if you do that, it will stop working. And it also smells, so other people will know.
Yep.
Okay. And you also have resistors. You're going to learn how to read resistors, how to read the values of the resistors based on a color code that is given. And the symbol that we are going to use for resistor is just a squiggly line, because, you know, you see the electrons couldn't go straight, right? They had to move around, resistance. And you're also going, for the imaging, you're also going to use a device that's called a phototransistor. What is a phototransistor? A transistor is a switch. Switch only lets electrons go once you have enough voltage. That's an electronic switch. A phototransistor is a device that works as a switch. It will let electrons go after a certain voltage, but it will also capture light and transform energy from light into electrons, and then increase the amount of electrons that you have. So you're going to use that. We're not going to, sadly, we're not going to study phototransistors here. But if you're interested in these things, read about phototransistors. Incredible devices. Okay, so let's start the definitions that we need for analyzing the circuits and how you can get to a circuit diagram. So what I'm going to do in this lecture and in our next circuit lecture might be tedious for some, very important for most of you. So stick to the method until you have the gut feeling of what you need to do for the circuits, okay? So when we analyze the circuit diagram, what we are going to be concerned with is how are the electrons moving as we apply voltage. So we are always going to be looking at the relation between current and voltage, because in our designs we can either design something to give current and then we will measure the voltage as a signal, or we give voltage and we measure the current as a signal. So we are always be looking between this relationship, voltage and current relationship. And when you look at the different elements, this very often is called the IV curve. Or the IV characteristics. In publications will be IV characteristics. In the lab jargon, IV curve. Okay, so let's say we have an element, and in this class, my elements will just be boxes for now. And in this box, we have some voltage that we are going to apply across it. So we are going to say, okay, there will be a voltage, which I'll call V element, that will be applied through this, across this device. And there will also be a current going through this element, which I'm calling I element. Where does this current come from? From the fact that this element is made of materials, and materials have tons of electrons. So if we manage to make the electrons move, there will be current. Okay? Do we ever run out of electrons? No. If there is a physical thing, this is full of electrons. Okay, and then we look how the voltage or how the current changes as we apply the other. So you might see a curve, an IV curve that looks something like this, which we're not going to study here. What is that curve for? It's a diode. Yeah, I just wanted to see who knew the diode. Beautiful device. Diode is almost like a switch, doesn't allow current in one direction, and one polarity of voltage only in the other direction. Okay, but what we want to study linear things. So in our IV curves, we are going to look at things that are a straight line going this way, or a straight line here. You apply voltage, the current doesn't. You have a different current, but the voltage is not changing. Or we are going to look at elements that display something like this with no current. Okay? But that IV curve could give you an idea of what's going to happen if you use that element in your circuit diagram. Okay. Let's start the definition of the elements that we'll have. First, a wire. So how do we draw a wire? A wire will be something like this. And we call a wire an element. So if we want to know the IV characteristics or the IV curve for this element, we are going to apply a voltage across it, V element. And we know that there will be a current going across, I element. And what happens in this situation? If I have a wire, and what's the voltage applied across this wire? Am I applying voltage? No. What's the voltage applied? 0. Okay. So if the voltage is 0, what's the current across this element? Well, we actually don't know. We can't say that it's 0 because that wire will be connected somewhere else, right? So that somewhere else, which is an external circuit, will actually set what the current is. So in a wire, and we are going to use wire as a model for our algorithms many times. The current is going to be set by the external circuit. External circuit. I told some of you that I write, so it goes slowly. Be patient. Okay. So how would I represent the IV curve then? I know that the voltage is 0, and I know that the current is going to be defined by something else. So if I had to draw a line here, and we know that it's going to be a line because we have linear circuits, what is it going to be? Do you have the answer or the question?
Oh, I had a question, sorry.
Huh?
I had a question, sorry.
Okay, so let me just get answers. What is it going to be?
Vertical line.
A vertical line that goes right through V equals 0. So it will be something like this. This is the IV characteristic of a wire. Go ahead, ask your question.
Why do we say that the current is set by the external circuit but not the voltage?
Yeah, very good question. Because you can have a wire that is connected to something else there, and you're not applying a voltage, that you know for sure, but you could still be having a current because there is a path somewhere else. Excellent question.
It's kind of like a live wire.
Hmm?
A live wire.
A live wire. Ouch. Very good. Next element, resistor. Resistor, we have more of a gut feeling for resistor, I think. So I'm going to draw the element here, and I'm going to be methodical because we are starting this method. So resistor will be the squiggly line here. resistor R, and we are going to apply a voltage across this resistor, which we're going to say V element. And there will be a current going through it, which is E element. Okay. Now, if I apply voltage through a resistor, there is current. Who knows how the relationship is? V equals IR. Okay, I will write here. Our friend here said that there is a relationship that says that V element, if the element is a resistor, is equal the resistance times the current passing through that element. Very good. And that is a law. What is this law called? Ohm's law.
Law.
Ohm's law. Very good. And how do I represent Ohm's law in the IV curve? What's the characteristics between voltage and current? If your element is a resistor, it's a line, yeah, that has some sort of slope. And that slope, or the inverse of that slope, gives you resistance from Ohm's law. Important, we are going to use many times. Okay. Can you just put your hand up if you had seen Ohm's law before? Great. Ohm's law. All right. Open circuit. Open circuit. Why do we need open circuits? Do we use open circuits in this class? All the time. Are they useful, Mickey?
Oh, yeah.
They make life easy, don't they?
Yep.
Open circuit. Open circuit, okay. We can still apply a voltage across this open circuit. And then, okay, what's our question here? What's the I element going to be here? If we have an open circuit, what is the value of the current? I element equals 0. Very good. And what's V element? It's hard to tell because it depends on everything else that is connected to. Very good. So V, we don't know. V is going to be set by the external circuit. Very good. And how is it going to look like in our IV plot? Current equals 0, and voltage depends on what is connected to. So a horizontal line that goes through I equals 0. Okay. Next, voltage sources. Voltage source.
Ooh.
Our batteries, or our little box in the lab, very expensive voltage source. Also could be a current source. Okay, voltage source. How are we going to represent the current, the voltage source? Now, the voltage source we represent as a little circle with plus minus. It always gives us a voltage that we know. So if you have a battery in your hand, you look at the battery, you know if it's a 1.5 volts, if it's 3 volts, if it's 9 volts, right? You know how much that voltage source is given. So that voltage that is set in your voltage source, and in the lab, you're going to pick the voltage, you're going to change the voltage through the diode, you're going to set that. It's going to be Vs, voltage of the source, okay? Now, in order to do this analysis, I'm going to put this element inside a box, transparent box here, because we do want to do the following. We want to say, for our analysis for the algorithms that we're going to be building, we're going to say there is a V element here, and there will be an I element. Okay? All right. So, in this case, the voltage source, what is V element? Vs. Very good. It's the voltage that is set by that voltage source. What's the current? I element. Who knows? Because that is set by the circuit. Very good. So, in this case, I element is going to be set by external circuit. But you can choose V. Okay. And our IV characteristics, how is that going to look like? A vertical line I hear, and that vertical line is going to cross the horizontal line where? Vs. Excellent. So it's going to look something like this, where this point here is Vs. Very good. So far, so good. We are just defining the elements that we are going to use later. Current source. Does anybody know an example of current source? I ask now because there are always questions about this. Seems to be a mysterious element. Anybody knows current source? Anybody? Where do you get a current source? Is it easy to make a current source?
It's harder.
It's harder.
Than the voltage source.
What classes do they need to take to learn to make a current source?
105?
105 starts, yeah. 105, 140, 140.
Yeah, 105, I think.
Yeah, 105. Okay, current source. You need transistors for current source, or you can also have a diode, a solar cell. Solar cell is current source. Takes light and produces current. Okay, so we don't see how to make a current source here, but in some examples we are going to use a current source. So current source, I'm going to write here outside of the box. It always gives us a fixed current value, which you're going to call IS, the current that's given by the source, just like the voltage source would give. And then for our analysis, we want to know what's V element and what's I element doing. So we say, okay, there is an a current flowing through this element, and we are going to apply a voltage across it in order to be able to analyze this circuit. In a current source, what's I element? IS, everybody agrees? Everybody sees why it's IS? Okay, and what's V element? Who knows? Because it's set by the external circuit. Okay, so I'm going to write here, V is set by external circuit. Very good. Okay, my next question to you is, how does the IV curve looks like for a current source? Oh, confident answers. Someone from the back. How does it look like? You can give me signals.
How does it look like?
Horizontal line, yeah? Horizontal line. And where is that horizontal line going to cross the vertical axis?
At IS.
IS. Oh, very good. It's so good when students participate. Okay, so far so good. Now, I have a question for you. does V element and I element always have to be positive? No, can be positive or negative, right? What would be a negative current? It goes the other way. Which other way? Well, we define, right? So I'll say, if students move from my right to my left, that's positive current. If students, electrons, move from my left to my right, that's negative current. That's it, opposite side. You need to define the sign. Very good. So that can be positive or negative. Now, let's do some other definitions for a circuit diagram. Here's an example of a circuit diagram. Doesn't matter if it's a resistor, a capacitor, even a diode, okay? A box, an electronic box, just like this one, okay? You don't need to know what's in there, but you can learn some definitions. So the first definition is a circuit diagram can have many nodes, and we are going to do node analysis in our next classes. So the first thing that you have to figure out is, how do I find the nodes and how many nodes are there in my diagram? So here is the definition of a node. Is the point where elements meet. Simple definition. So look at this diagram and tell me, how many nodes do we have in this diagram? You can talk to each other if you want to confer your answer, but how many nodes? I saw 4. I saw 1? No. How many? 4. 4. 4. Everybody
better get it
it's
right.
4? Yeah? I saw 2. 1, 2, 3. No. Okay. The way, if you don't know, you can pick an element. So let's say I'll choose this element here, and I'll start my node counting with this. So this is an element. So if I leave from this element, where do I meet another element? Oh, here. Okay. So 2 elements met here. So this must be a node. So I'll color this node here. Let me make this thicker so we can all see. Okay. So I'll color this node. So this I'll call node 1. Now,
Pink.
Pink?
Yeah.
Okay. Only for you, Mickey.
Thanks.
Now I am in this node here, and then I go from there and I go, ooh, oh, found an element. So that one is another node. Okay, next, green. Okay, I will go back to this element here and go, okay, I am in this element. I keep going here, keep going here, keep going here. Oh, now I have 2 ways to go. 2 ways to go. If I go here, I meet an element. Then if I go here, I meet an element. Oh, it's a long path. But that is a node right there. Okay. And finally, the 2 elements that we haven't visited yet.
Blue.
These 2. Yeah. So, how many nodes? 1, 2, 3, 4. Excellent. Now, junction. There's a question. I saw you running. Question.
Could we just count the number of elements because somehow they're going to get connected? Or
The number of elements? Oh, and then see how they are connected? No, because in some points you are going to get confused. Okay.
Why is node 4 one node? Wouldn't it be 2 because it connects to 2 different elements?
Because it was just, that's how the elements meet, right? Through this element here, I would say this element that I'll color blue will meet either element orange or the other element purple through this path. So it's where the elements meet through a wire, right? In our representation, the line is just a wire. So you have a wire that connects these elements, and that forms a node. Great question. I am sure other people were thinking the same. Okay, now the second definition here, junction. What's a junction? A junction is the point where different materials meet. So now I ask you, how many junctions do we have here? Five, 2. Well, it's more difficult to answer. Talk amongst each other. Read the definition. I'll give you 30 seconds. It's the point where different materials meet.
So it's between the two. So it could be, in this case it's 2, but it could be, yeah, anywhere along it.
Okay, how many? 8, 9,
7, 6,
7,
5.
100, 5. We don't know. Many junctions. Remember what I told you. Everything is made of materials, right? So in that little box, I can have a diode. A diode has at least 10 materials, right? So where you have these materials inside your element meeting, that's a junction. Okay, and then I have the wire that's made of copper, perhaps, and that copper attaches to the other material that is there forming my resistor, which is also made of many materials. Okay, so we don't know how many junctions, but you can assume that everywhere where you have different elements, there is a junction or many junctions. That's going to become very important by the end of this class. Okay? All right, that was a difficult question. I know. Now, potential energy. Potential energy is something that you are probably familiar with, because you see that a lot when you are learning mechanics, right, or classical physics. Potential energy, what does it mean? Okay, if you have, sometimes you learn in the concept of water tanks. So if you have 2 water tanks that are at the same level, there is no movement and they're going to stay in equilibrium. But if the water level in one tank is higher, then there's potential energy that is going to make water go from one tank to the other until you reach equilibrium, right? Potential energy is always related to high energy going to low energy. See where we are going here? I told you about electrons, high energy going to low energy. Well, we even use potential energy to make electricity, right? So if you have this high energy or the potential to move something, then you can have work done. All right, that's the physics part. Well, potential and voltage are related. And we mostly say voltage, but voltage is actually a measure of difference in potential. Okay, so if you have high energy, you will have a certain potential. And then you have another element that is somewhere else in your circuit that is a different energy and a different potential. The difference in potential between them is what we call voltage. That's why I had to correct our electron E there and say, okay, Miki, I'll go to the other side because you have to have the potential difference. And Miki said, but how do we start? Because we had to have different potential, right? So let's take, for example, the analogy of height. when we are hiking, we're climbing, you can say, okay, if I am here, I am at a point of high potential, and that is measured with respect to where I started, which is the ground, where you start your hike. But that's sometimes, measured at the sea level, right? Height is measured with respect to sea level. But you also could measure with respect to the bottom of the lake that was just by that mountain. So your reference is important. So you can say, oh, I climbed 10,000 meters, but you're measuring, you know, from the bottom of the lake to wherever you climbed. Reference is important. In electronics, reference is going to be important too, because voltage is difference in potential. So we always have to know where our reference is. And reference, the jargon is ground. When you hear, oh, did you ground this, or where's the ground, is the reference node, where you're saying, okay, I was starting from here. Okay, so let's start transitioning from hiking, which certainly good to do after long lectures, but to charges. So here, what I'm representing, and I think this from your note 11, so if you read the note, or when you read the note, you'll see that. So we are setting a reference. In this case, the reference 0 here was ground. So you see here that a potential 2 is here at 0. That's our potential. And this path here for climbing, for sure we have to spend energy. So it's represented here as an element. Could be a resistor, could be a resistor with a high resistance if you're climbing, could be a resistor with less resistance if there is a lift to go from here to there. And then this lower part here is representing the work that it would take to cover this ground, okay, from the reference. So when I said positive, negative, if I'm setting my reference over here, but I want to measure something below, that would be negative, right? Negative potential. While if I want to measure something above, my reference would be positive. So in this diagram, simple diagram that we have here, we have the following. We have U1, U2, and U3, which are points in our diagram that represent potentials. Make sense? Okay, now voltage is the difference in potential. So I ask you, what is voltage 1? Voltage 1 here is represented here. What's voltage 1? With respect to the potentials, voltage is different in potentials. Voltage 1 is taking 2 points in this diagram. Point that has potential U1 and point that has potential U2. So what's voltage 1? U1 minus U2. I know, it sounds easy. What's V2? U2 minus E3. Where am I looking here? Here is U2, here is U3, and I'm looking at the difference here, V2, which is voltage, okay? And what's V total? Could be U1, U1 minus U3, or you could also write that V total is, yeah, V1 plus V2. Very good. But we also know what's the value of V total, because that diagram is telling you what's the value of V total. What is it? BS. Yeah, go ahead and ask your question. You will have to be loud. Yeah. This diagram here should say X2.
Oh, okay. That was my question.
Yeah.
About the X's. Thank you.
Because it's bringing like the height to voltage. Yeah. So at the top we have the equivalent of X1 here in our drawing. U2 is the reference, and then X2, which should say there, is the reference underwater. Thank you.
So in the, like below the circuit, shouldn't it be U1 minus U2 plus U2 minus U3?
You could do the total difference, or you could go the parts. Yeah, which is what we did here. So here we did several ways of finding V total. Here we looked at the potential difference. Here we did as the sum of V2. And here we said it's Vs. Did I answer your question? Or you were saying this should be?
Like on the...
Should be plus.
Like on the top?
The plus?
Like shouldn't U1 minus U2 plus U2 minus U3? Below the circuit, right below it.
In the diagram.
In the diagram. Yep. In this one? I don't know where you see. Oh, yeah. It should. Yes, okay. I will make a note. I thought it was something that these are from the notes. Please check the notes, and if it's wrong, we should fix. I'll check it too. Thank you. I wasn't looking at that diagram. Okay, makes sense? Okay. So, next, let's start some rules. We have some time, still 6 minutes. Let's start by looking at some circuits. So, I'm going to draw a very simple circuit where we have a voltage source and a resistor connected this way. And in this diagram, I know that resistor has a value of R, and I know that the voltage source has a value of Vs. Now, first question I have for you, how many elements do I have in this circuit? 2? 2? 4. 4. Why? Let me mark them. We have a voltage source, we have a wire, we have a resistor, and we have another wire. Okay, so I will be consistent to what I was doing before, which is, here I have V element 1, here I'll have V element 2, across this I'll have V element 3, and here I'll have V element 4. Okay, so in this law, which is the Kirchhoff's voltage law, it says the sum of the voltages across the elements in a loop is equal to 0. Do we have a loop here? Definitely. So if we go around the loop here, the sum of the voltages should be equal 0. So let's write this equation together. I'll start with V element 1. So I'm going here from minus to plus. I'll say V element 1. Now I go from plus to minus. What do I say here? Minus V element 2. Plus to minus, minus V element 3. Plus to minus, minus V element 4 equals to 0. The sum will be equal to 0. In diagrams, or what we were talking before, what does this mean? I have a voltage source. That voltage source is applying some voltage, which looks like this, V element 1, right? And then I have here plus or minus V element 2, plus or minus V element 3, plus or minus V element 4. And I'm saying, if I go from here all the way here, the sum is going to be 0. So I have 2 questions for you. First question, what's V element 1? What's V element 1? Vs. V element 1 equals Vs. Now, you can take your phones and answer the question here. We will go over
30 seconds.
Huh?
30 seconds.
30 seconds, yeah, because the class is almost over. And I will go and responses. Let's see if I have connectivity. 21, 25, come on. You can talk to it. The question is...
Do you need to put the, maybe put the
what
QR code
is
again? QR code again? QR code?
Sorry. There it is. And the question there is, what is the voltage across element 3?
Do you vote? Do you vote?
Good?
You exercised your
Everybody got
democratic right to vote? That's pretty cool.
Okay, the first time you're not supposed to talk, but that's okay.
Yeah, don't talk.
Okay, let's see. Oh, file reload. How many? Oh, 200.
Ooh,
oh,
wow,
shall we
pretty good.
take a look?
Oh.
Okay. So we have 24% saying all of the above. Now we have 34% saying Vs, which was the voltage in element 1. Some people said R times I, and a few people said V element 2. Okay. So, 30 seconds to talk. Let me show you the diagram again. There's the diagram. Think. Huh? You need to delete the answers. Here. Okay. And then they reply again. Okay. All right. We are almost out of time. So cast your vote and I will give you the answer. 10 seconds.
9, 8, 7, 6, 5, 4, 3, 2, 1.